Hi, my name is Jewel, and this is my interactive advanced concept presentation on the nuclear bomb and the chemistry that goes behind it. So first I'm going to discuss the nuclei and the nuclear reactions and what exactly that entails. So with the exception of hydrogen, all nuclei contain protons and neutrons. The image on the left is a basic depiction of a nucleus that contains 3 neutrons in green and then 3 protons in the red, and then you can also see the blue electrons that are in orbit. So some of these nuclei are unstable and they'll undergo something called radioactive decay. And they do this by emitting particles, which can be seen in the table on the right side. So the spontaneous emission of these particles is referred to as radioactive decay. So elements that have an atomic number that's greater than 83, which means they have more than 83 protons in their nucleus, these elements would be considered unstable and thus radioactive. So the most common subatomic particles that participate in these nuclear reactions are the proton, the neutron, alpha particle, beta particle, positron, and gamma rays. So again, if you reference the table on the right side, you can see these different types of reactions. So just going to quickly talk through those reactions. The alpha decay, that involves an alpha particle, which is a helium nucleus, which is then emitted by some radioactive substance. Beta decay is going to be the emission of an electron, which is moving at high speeds with high energy. Gamma decay is going to involve the emission of a high energy electromagnetic radiation, and this is produced when the nucleus changes or goes from a higher energy level to a lower one. And then the positron emission involves a positively charged electron. Electron capture involves an electron, as the name suggests, and it's going to be absorbed by that substance. All right, now I'm going to compare radioactive decay and talk more about nuclear transmutation. So nuclear transmutation is different from radioactive decay. So the radioactive decay that I discussed in the last slide is naturally and spontaneously occurring. However, with nuclear transmutation, it's different because it's brought about by the collision of 2 particles. So in 1919, Rutherford introduced the possibility of artificially producing radioactivity when he bombarded a nitrogen sample with alpha particles, and this gave him oxygen-17 isotope and proton emission. So with this possibility open to the world of science, particle accelerators came into play, and this will be a big part of how nuclear bombs came into play. So the particle accelerator. Particle accelerators made it possible to synthesize transuranium elements, which are elements that have an atomic number greater than 92. Particle accelerators use electric and magnetic fields to increase the kinetic energy of a charged species projectile to force a reaction. So the polarity is alternating on different plates, and this causes particles to accelerate in a spiral path. When it has enough energy, it's then guided out of the accelerator and into a collision with the target substance. So many synthetic isotopes can be prepared with neutrons as projectile, which that would take out opposite charges from the equation. But with the particle accelerator, this allows scientists to pass through this obstacle of using charged particles. So most importantly, in the context of this presentation and the topic, the particle accelerator played a critical role in the research leading up to the nuclear bomb. So Ernest Lawrence developed a cyclotron, which is a type of particle accelerator. He eventually converted this into a mass spectrometer, and this was designed to separate uranium. So Lawrence's cyclotron and then eventual mass spectrometer were instrumental in the production of fissionable isotopes and the ultimate success of the infamous Manhattan Project. So nuclear fission. Nuclear fission is the process in which a heavy nucleus that has a mass number greater than 200, it breaks up into smaller nuclei. So a large amount of energy is going to be released in this process, and since that heavy nucleus is substantially less stable than its products, that's going to account for all of that large energy. So the nuclear fission of uranium-235 is what we're going to be focusing on, and it's particularly significant in the context of this presentation. So not only because of the immense amount of energy that's released from the fission reaction of uranium-235, this is very important because more neutrons are produced than are originally captured. So this creates a nuclear chain and allows this process to continue going. So in order for this reaction to occur, there needs to be enough uranium-235 present to capture the additional neutrons. And this amount is going to be known as the critical mass. If there's anything less than the critical mass, or the mass is subcritical, neutrons will escape and the chain reaction will not occur. So the nuclear bomb. The two most famous nuclear bombs are going to be Little Boy and Fat Boy, which can be seen in the slide. They were used in World War II, as we all know. So nuclear atomic bombs are not assembled with a critical mass already present. So in Little Boy, the uranium-235 is kept in a subcritical configuration. The Little Boy uses a gun-type mechanism to achieve this supercritical mass by firing a piece of uranium-235 into another. And then Fat Man, which uses plutonium-235, had to use a different mechanism due to complications with the use of the plutonium-240. Or with the use of plutonium-235, which was caused by plutonium-240 that was produced when the plutonium was in the reactor. So instead of a gun-type mechanism, Fat Man used an implosion mechanism. So the fissile material is placed into a sphere with a slightly less than critical mass, and then layers of high explosives are carefully placed surrounding the sphere, and then when they're detonated, that force compresses the fissile material into a smaller volume, allowing for it to reach supercritical mass, and then thus allowing the nuclear fission reaction to occur. So that is my presentation on nuclear bombs and the kind of chemistry, nuclear fission, that is critical behind the use and creation of nuclear bombs. Thank you for watching.